Afternoon, everyone. My name is Oumarou Moussa Bola. I'm a second-year PhD candidate working on aircraft trajectory optimization with sustainable aviation fuel for climate impact mitigation. So the main motivation of my PhD is climate change. As you know, the imperative to address climate change has reached a critical juncture, and the global target aim to limit Earth temperature increase to well below 2 degrees Celsius above below pre-industrial level, with a more stringent goal of limiting or staying at 1.5 degrees Celsius below pre-industrial level. So the year 2024 was the first time we actually crossed that threshold of the 2015 Paris Agreement of staying at 1.5 degrees Celsius, and which means the aviation sector, or we need comprehensive mitigation measures in order to avoid irreversible damages. So the aviation contributes to climate change by emitting various pollutants such as carbon dioxide up to 34% and non-CO2 effect 2/3, which is 66%. And the non-CO2, amongst the non-CO2, we have contrail, which is just short for condensation trails. They can have cooling or warming effect depending on the long wave or short wave radiation. So we have also the NOx-induced ozone and methane and water vapor, amongst other things. All in all, the sector currently accounts for 10% of transport sector emission, 2 to 3% of the global CO2 emission, and 3 to 5% of the total anthropogenic forcing. So there are several mitigation pathways actually that are being investigated by the aviation stakeholders. Amongst them, we have the CO2 mitigation pathway, and then also the non-CO2 mitigation pathways. Amongst them CO2 mitigation pathways, we have technological solutions such as the hybrid electric aircraft or the hydrogen-powered aircraft. We also have the sustainable aviation fuel, such as the drop-in or the non-drop-in. The drop-in is the sustainable aviation, the SAF, and the hydrogen is the non-drop-in fuel, or market-based measure, which are some sort of taxation. It means you fly, you pollute, and then you pay for it. So on the other hand, and these CO2 also, they can be beneficial for also non-CO2 effect, and they are relatively medium to long-term measures. The non-CO2 effect, on the other hand, they have a strong dependency on the time of the location of emission, which means flight planning can be a promising measures in order to mitigate these non-CO2 effect. And it's actually feasible with existing infrastructure, and these are relatively short-term measures. My PhD, but there is a limitation with the flight planning, is like at larger scale. Flight rerouting also may increase air traffic complexity, which can induce or compromise operational feasibility. My thesis is about combining or integrating alternative aviation fuel and operational flight planning. So what are the benefits and limitations of SAF? Benefit and limitation of SAF. SAF, compared to kerosene, when you fly with SAF, you have a cleaner burning. We have a cleaner burning, which means because of its lower aromatic content, and also you have a reduced number of soot, which means at later stage, when the water vapor condenses, you have an increased sizes of the soot particles, which has a repercussion on the number of initial ice water concentration, which again, or in the end, contribute to reduce the lifetime of contrail in case you form a contrail while flying through an ice supersaturated region. And all in all, the SAF can actually reduce the CO2 life cycle emission, well-to-wake CO2 emission on 94%, up to 2.5% of the fuel flow. It can also mitigate potentially, if you want, mitigate the non-CO2 effect, but its limitation is mainly the availability. Currently in Europe, the maximum availability of SAF is only 2%. So now, going into the literature, the most recent studies up to 2026 have shown that currently there are no studies that have combined climate-optimized flight planning with SAF. And all the flight planning methodologies were based on direct optimal control genetic algorithm going to augmented random search up to fast marching tree. The main identified research gaps are therefore existing, we know that there are no studies that I have just mentioned. There are no studies that have looked into climate optimized flight planning with kerosene. We have a need for accurate SAF emission quantification and climate impact estimation. And also, no study have still investigated the potential of SAF and flight planning to address both the CO2 and non-CO2 effect of aviation. So now, the main research objective of my thesis are threefold. The first one, climate optimized flight planning with SAF, carrying out and then the second one, conducting a large-scale analysis of the mitigation potential of SAF and climate-optimized flight planning in order to inform and support evidence-based policy decision and come up with KPIs, key performance indicators. So, and the third one was to develop an AI-based aircraft trajectory optimization that increases the computational efficiency of the state-of-the-art optimizer, which leads us to the research question of my research. How can we effectively utilize SAF and climate optimized flight planning to maximize the climate benefits while ensuring operational feasibility and accounting for current SAF limitation? So now let's come to the general formulation of the problem. To generate, yes. Okay, to generate, yeah. To generate a feasible and efficient trajectory between any two destination pairs, our objective is to go from the cost-optimal trajectory to climate-optimal trajectory by trying to avoid climate hotspot, which are in this study, or in this case, warming countries, but they can also be cooling countries, right? And the problem is formulated in general as a stochastic optimal control problem. And we have the aircraft dynamical problem, aircraft dynamical model, which we model as a point mass, aircraft point mass model. The objective function subjected to the operational constraint and flight envelope limitation. So in our case, the flight planning objective is simply the sum of the operating cost and climate optimized climate impact estimate, which we estimate using ACCF or Contrail Cyrus prediction model. So in line with the objective one, which is climate optimized flight planning with SAF, the methodology is the following. We start, the inputs variables are actually the weather data, origin, destination, the aircraft type, the airspace structure, which we include to estimate the climate effect using gradient COSIP. And the first input and the input of gradient COSIP are also integrated into ROOST, which is a robust optimization of structured trajectory. And then we have the optimized trajectory in the end. So now, what is ROOST? Actually, in a nutshell, ROOST is just a technique for flight planning that integrates horizontal and vertical decision making, and then the optimization also is based on augmented random search. So a single case analysis, these are a result of a single case analysis on January 2nd, 2023, optimized using ROOST on a flight from Frankfurt to Kiev, considering three types of fuel blends. The kerosene, 50% SAF, blended with kerosene, and then the 100% SAF with an A320 aircraft. And then the climate impact estimation model used was the gradient COSIP. The objective function here, the function to be minimized is just the following. We have the expectation of the operating cost plus the expectation of the contrail net radiative forcing. So here we can see the vertical profile for this specific case or this specific scenario. I should reinforce. We can see that the vertical profile shows higher cruise altitude for the cost optimal trajectory and the climate optimal trajectory of SAF, 100% SAF. And then for the flight operated with 50% SAF and full kerosene, it tends to fly at slightly lower altitude. So, and here we can see the contrail evolution map of this experiment. And we can see that for the cost optimal trajectory, with kerosene, we are actually forming more contrail compared to when, as we increase the SAF, we are also actually reducing the amount of contrail generated. And with we can see the similar trend whilst looking into the climate optimal contrail evolution map. So Here you have the Pareto front, and for example, you can see that with just 3%, if we allow a 3% increase in operating costs, we can mitigate of up to 90% of the contrail. We can mitigate 90% of the contrail with just 3% increase in operating costs. Now, here, carrying out several single case analysis if you want, in series, in series, January 2nd, 14th of March, and 18th of March 2023. Why? It's because I wanted to look into daily variability and also seasonality, because some of the days you don't have a lot of incoming solar radiation, which means you will not form cooling contrails. So it was a clear decision of looking into March. We are forming cooling contrail. We can see that for the cost optimal trajectory.
Oumarou, you have already consumed 11 minutes, so please finish.
Okay. So the single cases analysis is not actually doing the optimization of the single case analysis cannot give us a comprehensive. We cannot have a comprehensive or evidence-based conclusion to say, okay, going with this such blend of SAF is actually feasible. Of it can provide a certain benefit, which leads us to performing a larger scale analysis in order to see actually the clear benefit of flying with SAF compared to kerosene. Here, our idea is to implement a decision-making framework. Here, we input the...
Oumarou, please finish.
Okay. Decision-making framework is based on actually mixed integer linear programming, and then we consider several bending ratio at SAF, and here you have the vector of performance variable with respect to the K flight and associated with the routing and blending ratio of SAF. So I have to...
Please skip and finish.
Okay.
Already 12 minutes.
Okay, so the aggregated analysis, what it shows, all in all, it shows that with only 1% of SAF, we can mitigate the business as usual trajectory up to 35% of the contrails. The climate optimal, by just allowing 0.045% of simple operating costs, you can mitigate up to 75% just with 1% SAF availability. And with 100, with the second climate optimal, we can already mitigate 100% of.
Oumarou, please go to the conclusions. Finish.
Okay.
Sorry, but I already told you.
Okay.
I'm sorry.
Okay. But with 20%, but this is really interesting because with 20%, we see the saturation. It means adding more SAF or incentivizing the production of more SAF will not add any climatic benefit.
I understand it's very interesting, but...
So the proposed solution here...
Please finish.
So, okay, this is ongoing work on the, in line with the third objective, which consists of developing an AI-based trajectory optimizer. So these are my research contributions. So these are, if you want, my achievement and contribution throughout my PhD, 1 year and 6 months now. I have a paper almost ready for submission, scientific, I attended 2 conferences, scholarship, mentorship, participation in European projects, and the courses and workshop. Thank you very much.